So is my screen visible, everyone?
Yes,
Okay. Good morning, good afternoon, and good evening, everyone. Thank you once again for giving me another opportunity. And today's presentation is going to be slightly different, but it is just going to be slightly different from what we went through in study jam 2. So most of the content is going to be the same, but I have added just a few information in the end. I hope this is helpful for you all. And thank you so much again, everyone, for giving me this opportunity. Let's dive into the topic. So, what data do we classify as big data? So, big data is a concept which is very famous or very constantly used nowadays. So, big data is something that doesn't fit into your computer. So, you have something to execute, you have some computational process to be done on certain data, which isn't completely done by your computer. Just one computer isn't enough. So, we see big data consists of three main characteristics. They are volume, velocity, and variety. So, we all know about Moore's law, and it says the number of transistors on a microchip doubles every 2 years, though the cost of computers is halved. So, what's happening is we get more devices and we collect more information, and the volume is increasing. So, since the data collected is increased, actually, the increase is in several folds. Even a single user using a single device can create several data with several applications running simultaneously. Because in the same phone, we use YouTube, we upload content, and we use WhatsApp, we use email, messaging, Facebook Messenger, Instagram, and so many applications in one single device. So imagine a person owns several devices and the number of devices owned is increasing. So I would say data is exponentially increasing. And the quantity of data that is needed to be stored also increases since the data generated has to be stored nowadays due to analytics reasons. So here is where we have the concept of scaling up and scaling out. We'll talk about it in a bit. Then we have the velocity. Velocity refers to the speed with which the data we are collecting travels into the system for getting processed, because we are collecting all the data to process. The rate at which the data is collected has changed over the years. So a few years ago, retailers just use the data like we checked out. So only the checking out data was important a few years ago. Based on the checking out information, they decided whether to purchase specific product or not. But nowadays, there is something which is very important, that is cart abandonment rate. So what happens is you try to buy something on Amazon, but for some reason you don't buy it. Everyone is concerned about it. If you are not buying something, that is going to be a loss for the company, whoever is selling whatever product you are abandoning. Either they focus on improving the cost, or maybe they try to improve the brand name, and there are so many other factors into it. So in processing the big data, velocity is the speed at which the data comes in, and it can be categorized into two. Oops, sorry. So one is stream processing and the other one is feedback loop processing. So let us see what stream processing is. When data enters a system, the data is analyzed as it enters, and they are filtered continuously, and it is almost done instantaneously. This filtering is done to decide whether the data we have collected is good to keep or we have to discard it. Sometimes, it becomes impossible to store all the data. With respect to feedback loop processing, this is very similar to analytical processing. Here, all the data entered is stored and then analyzed to provide actionable insights. So, the process of capturing the data, processing it into usable information, and then acting on that information is called the feedback loop. Feedback loop processing um, to provide immediate information requires analyzing large amounts of data, and it has to be done quickly so that the results of the analysis can be a part of the product delivered to the user, of course, in real time. So, a good example here is the recommendation system, and the examples I have quoted here are Amazon. Actually, Amazon and Netflix, but I have put here only Amazon. So, imagine you are purchasing a book. So, what happens is all data about you is collected. What data about you is collected? Your profile, your information, what video or what book you are requesting. And then, based on your history of purchasing things, and based on the other people who have purchased the same type of books or same type of videos, an analysis is made, and then um, a list of recommendation video is added to the user request. So what happens as a result? The user gets what he or she requested along with the recommendations. So the key difference between two processing, that is stream processing and feedback loop processing, is stream processing is input focused and feedback loop processing is output focused. So here in stream processing, it is decided whether the data is required or not. In feedback loop processing, we have the data, but we are generating insights out of it. And then we have variety. So variety refers to the structure of the collected data. Data generally is of two types. One is structured, other one is unstructured. Structured data conforms to specific data models or data standards, whereas unstructured data doesn't um, conform to any norms. So let us see some examples of unstructured data. We have maps, we have photos, videos, emails, tweets, etc. And most of these unstructured data is stored as a blob storage. We have other types of V's here. Totally, we have 7 V's. So in addition to the three V's, what we see here is variability. Variability is, imagine we have certain words. The same word can have different meanings depending on the context. So sometimes we get confused with variety and variability, thinking they are similar terms, but they mean distinctly different things in big data. Variety is about the structure, how structurally it is different, and variability is the difference in meaning. And the next one is veracity. It refers to the trustworthiness of the data. Trustworthiness here, we can consider it as a concept of relevancy, because for example, data collected before election might not be pertinent to after election data. And sometimes people collect opinion based on incidents happening, but the opinion keeps changing. So whatever you collected in the past cannot be applied in the current situation. For example, um, consider the surge in demand for face masks are disinfectants, which happened a year ago and right now. So you cannot use that historical data to determine your demand at this point, because a year ago prices were exorbitant and the product was in huge demand, but right now it is not. And the next one is viability. Viability, the other name is value. and it refers to the depth or how deep the data can be analyzed. So the data has to have a value. Just because a data is collected doesn't mean that it has to be very useful in decision making. Data is just data. How useful it is depends on how much insights we are going to get out of it. So viability is very important. And the final V, the seventh V, is visualization. Of course, visualization is very important. It is going to be visualizable because it visualization makes data more understandable. Sometimes, you know what happens, huge volumes of data can leave decision makers get stuck with data but with little understanding of what these data actually mean or what the fact actually is. Visualization is a way of presenting the facts so that decision makers like you and me can comprehend the correct meaning, the right meaning, and we get the most desired information or the most useful information to gain useful insights and actionable and useful outcomes of the analysis. So there is something called polyglot persistence. Polyglot persistence actually refers to coexistence of variety of data storage. The same organization might have um, a storage a storage platform for both structured and unstructured data. And nowadays, this is a mandatory thing because every data, every company collects. Usually, we always say transaction data, such that a customer purchases something and he pays, he get back something, he takes away the goods. So there will be an involvement of the inventory and cash comes in. The customer is um, debited. So all the customer is credited. So all these things happens, right? So it is not just these transaction data. We also need information like maybe the customer is constantly monitored. In any store, a customer is monitored. So we also know how good a customer is going to be because only based on certain data which we obtain from unstructured data, several important decisions are taking place. And we all would have wondered like where exactly the big data comes from. So it comes from several sources such as like existing databases, the old documents, the media we are using, the cloud platforms currently, the web, the browsing data, IoT, of course, because in even in traffic we have cameras everywhere, and it is going to collect information. And if you are going to exercise, you have that Fitbit or iWatch, which is going to monitor your heartbeat, your activity level, etc. And you have the social media, social influences, activity generated data, data warehouse appliances. So um, they can be clubbed into four main categories. One is sensors or meters activity, social interactions, business transactions, and broadcastings. So broadcasting, so we are recording a video right now and it is going to be uploaded in YouTube. So there is going to be an analysis that is going to be performed simultaneously. There is also a data here. So how many views a specific video has, how long a speaker has spoken, how long the video is, or how many videos the user uploaded. So this is an example of how data can be um, generated with this broadcasting. And then generally speaking, we have the business transactions, and we know the social interactions such as Facebook, Instagram, all the likes and other information. So this is a picture. I haven't changed anything since the last presentation. So big data is a relative term. Right now, we have at least a laptop which has 160, 160 or maybe like 250 GB of storage. But a few years ago, Even 1 MB was a huge, they needed a huge device to store that. So the processing has improved nowadays. So if a small instrument, even a phone which can have almost like 32 GB of expandable, not 32, actually it is 64 GB currently, they even have more than that. So there's a huge difference. 10 years ago, when you purchased for memory chip, a memory card, it's going to be like 100 MB maybe, or 500 MB, and with the same size or even smaller than the size, we have more storage right now available. So it's a relative term. What we consider big data might not be big data tomorrow, because if the processing speed and the processing ability of the computers we are using increases, the concept of big data also undergoes some sort of a development. So we discussed about scaling up and scaling out a few minutes ago with regards to volume. Scaling up is improving the capabilities of a single system or single computer, but whereas scaling out is having multiple attachments or multiple computers parallelly available. So if you have a single computer and you are not satisfied with the memory, you can go ahead and you scale up your single system, or you can connect several computers with low computing capabilities together, chain together to perform parallelly. This is actually going to be the concept of big data processing with Hadoop. So one thing I want to mention here, so in the previous presentation, I mentioned only Java-based framework. Yeah, it is based on Scala, but Scala is written in Java, which I forgot to mention. So I wanted to include this here. So Hadoop has become the de facto standard for most big data storage and big data processing. As you all know, Hadoop is not a database or a language, but it is a framework, and it is it is a Java-based framework, and this is for distributing and processing very large data sets across several clusters of computing devices or computers. We can consider so this is a simple thing that came to my mind suddenly. So imagine you store um, a, I'm not sure if this is a very apt example, but I just wanted to give you. You keep a bottle of water in the refrigerator, or you can keep several small bottles of water in the refrigerator. If something happens, if someone breaks a bottle, the rest of the bottles are going to help you. So this is behind the concept of cluster computing. I will explain you a bit later. And Hadoop is it is a low-level distributed file processing system. What does low-level distributed file system means? It can be used directly for data storage, and it can also be used for computing when we use MapReduce. So MapReduce is a model, and it supports processing of the data. So let us look at what the basis behind the HDFS storage system. So whenever data is collected, data is organized into physical blocks, small chunks of memory, because it is not going to be a big block storage. It's going to be like small blocks. So with respect to other storages, first of all, in file storage, it is going to be like 512 bytes in a computer. So whatever data is collected or whatever data you save in your computer, it's going to be stored in small chunks. And each of these blocks will have a reference number. So whenever you're searching for a file or something, it is going to say, okay, these blocks of memory is going to have file related to your query. Maybe you look for Udacity course materials. You store it in a computer. So it is not going to be stored as a single file. It's going to be in small blocks of 512 bytes each. In Oracle, it is 8 kilobytes of physical blocks. What happens in HDFS is data is organized into um, physical blocks, which is 64 MB default block size. And the good thing about it is you can scale it up. So, what happens when you scale it up? Whenever you do batch processing, it's going to be like, processed quickly. And one of the benefits of Hadoop is processing data as a batch. And then, of course, we know um, it's going to be fault tolerant because the data which we are storing is going to be stored in several computers. No, not in instead of just one computer, it's going to be stored in several. And in all of these, the data is going to be replicated. It gives a fault tolerant model. What happens if one of these computers fails? The others are going to support you as a backup. Let us look into details of the HDFS architecture. So we know that HDFS is a distributed, highly distributed and fault tolerant file storage system, and it can manage large amount of data at high speeds. So we know it is going to withstand velocity and volume. So if you have just a local computer, it is going to be just that computer. Whatever CPU or RAM that is going to use, we are going to utilize only that. But if we use a distributed system, we have a main computer and there are several computers attached to it. So the whatever data you're going to give is going to be shared between all these devices. And it uses several types of nodes. One is client node, other one is name node, and the other one is data node. Client node is from where the input is going to be fed, and the name node contains some metadata. Metadata can be the file name, what block numbers contains a specific information, like the example I gave you a few minutes ago. And there is a concept called replication factor. Replication factors determines how many copies are going to be made when we are going to decide to replicate the data. Since we know this is a fault tolerant uh, architecture, we have a data. For example, we have some data given, data X given, and we want to make sure the data is safe. And we also specify how many copies of the data are kept. If you say 3 copies, then it is going to be copied in 3 computers. And based on the information given, the name node decides which data node the thing has to be stored. So data node, only the data nodes you see here, like there are several computers, they are the data nodes, and they store the um, actual files in the Hadoop distributed file system. And these files, these you can see like 5 computers chained together, and these files are subdivided into small blocks of storages, and they are replicated across these um, group of this set of computers for fault tolerance. And usually the replication factor is 3, that is the default, but based on your availability or your capability, you can have it more, you can scale it up, you can scale it out, which means like any data stored is stored in at least 3 devices, and it can be stored in several devices. If you want to um, ensure it is safe, you can have even more. So if one fails, the rest others are going to support you with the information. And name node are all these computers. And oh sorry, name node is the single computer to which the group of computers are clubbed into. So name node only contains the metadata of the file system. And one thing you have to know understand is name node doesn't store any data. And the metadata stored in the name node is going to be very simple, it's going to be very small, and made sure it is recovered easily. So keeping this metadata small allows the name node to hold all the metadata in memory to reduce disk access. So what happens? The performance improves. Why are we more concerned about the performance of the name node? Because in every cluster, we are going to have one name node and several data nodes. Since there is going to be just one, we have to make sure it is safe. If you abuses it with heavy data, it's going to fail. It is not like the data nodes. In data nodes, if one fails, other is going to help you. So someone asked the same question during the previous session, study jam 2, about what happens if the name node fails. For that, okay, so for that I just put it the name worst case scenario. What happens? We have a secondary name node that that actually replicates data of the name node. So in case the name node fails, the secondary name node is going to help you. So what happens in a client mode? What is client mode? So the client node makes request to the file system. If the client wants to read or write something, it it contacts the name node. And when the client node needs to create a new file, it talks to the name node. It communicates with the name node. And the name node adds a file name to the metadata. It adds file name because it only stores metadata, and metadata contains file names. And then based upon it is going to write a new file. So it has to figure out which of these name nodes has enough space. So it determines where to write the data. So it has to determine which block it has to write. So block number is taken into block ID is taken into consideration, and it also determines which block in which of these nodes would save the data. That is what it does. And then it gives all the information to the client. The client node contacts the first data node. So you see the green arrow here. It is going to contact the first data node specified by the name node. And then it starts to write file on this. And then the client node contacts the first, okay. Um, and it simultaneously contacts the second data node. So what happens here? Here, after these nodes are the first node, after getting written down, it also has the information of how many replications have to be made. So they contact the other data nodes to make sure the other copies are maintained. So the data node contacts other data nodes to which the data needs to be replicated, and they have the information. And each data node connects to the next data nodes, and the process continues until the replication of the file is complete, until the replication factor is met. So as of now, we have seen how writing a data request is processed here. This is also similar to reading the data. If it wants to read a specific file, the client approaches the name node, and the name node looks at which of these data nodes has the information. If it has information, which exact block has the information, and then it conveys to the client, and then client goes ahead and reads whatever it wants to read. So it is similar to the same as writing the file. So see, for writing the file, the client contacts, and I will talk about the job tracker and task tracker in the next step. So since we have the data node and name node, there has to be some kind of connection in between them, right? So how would you know whether this data node is available or not? So there are two types of communication available. One is block report and heartbeat. Block report is sent every 6 hours, and it gives the name node the information about what data it is storing, where it is storing, which block it has all the information, and how much of free space it has. So it is reported every 6 hours. Based on that, the name node will decide which block to store the next chunk of data received. And there is another thing called heartbeat, and happens every 3 seconds. So the data node and name node are connected. If something happens to the data node, the heartbeat will not reach. So the name node decides, okay, this data node is dead. Let me look at something else. So it tells it's alive, like how our heartbeat tells we are alive. The same thing applies in HDFS. So this is the architecture of HDFS. So I mentioned the analogy previous time too. I want to tell you here. So look at the customer. The customer is a client. He needs to withdraw money or maybe deposit money in the bank. So you can consider depositing money as writing files or withdrawing money as reading the file. So it goes to the name node. Name node is like the receptionist. The receptionist only holds data of where the client should go, which teller the client should go in order to successfully process the information. So um, this receptionist will have only the information of which teller to go. So the customer goes to the exact teller, and each of this teller is like a data node. They go to data node and do the transaction. So data node is where the data is stored. Data node is where the teller location is where the cash is stored. Here we never pay the receptionist. Similarly, the name node never accepts any data. Name node doesn't store any data. And sometimes when a receptionist has to go on a break, there will be other person in the front desk to take care, to cover up for this shift probably. So that is similar to what happens. We have map reduce here. So map reduce, the name itself tells you that we are going to map something, and finally the output is going to be reduced. Just imagine you want to build a house. You're not just going to um, give the input to just one person. There will be electrician working, there will be plumbers working, there will be like mason working on the construction of the building. So the task is distributed to so many people, and in the end everything is clubbed together and you get a home. That is similar in case of MapReduce. And MapReduce is for processing large data sets, and it uses the concept of divide and conquer. MapReduce, which similar to the example I gave you, it takes a complex task, breaks it into several smaller subtasks. It does the subtask, and the thing is, all these subtasks are, you see the map task here, all this happen at the same time. And then the result is in the form of a key value pair, and then they are clubbed together as a combined input. So each task will have its own subtask. It depends upon what task we are assigning. And for these, we have the job trackers and task trackers. So this is the one I was mentioning with this image. We have the job tracker and the task tracker. So what happens in a MapReduce process? So there is a client node, and it starts a MapReduce request to the job tracker. So job tracker is on the name node, and the job tracker communicates to the name node, each of these name nodes, to find which data nodes contain the block that should be processed for this specific task the client assigns. And then that the job tracker finds the available task trackers. Why available task trackers? Usually, most of the task trackers are busy doing some MapReduce functions. So, in a single node, a task tracker could be performing operations of other tasks too. So, we know that here all these activities happen simultaneously. So, which job tracker will find the task tracker which is available or whichever is not available. So, it has to which tracker is free, it has to find out. And then the job tracker tells the task trackers to complete that node specific task. So each of these nodes will have a specific task going on. And these job trackers monitor uh, task trackers. Like this is like a master for these task trackers, and job tracker has to make sure there are no failures here. In case there is a failure here, how do you find the failure? We know that there is a heartbeat that goes from this data node to um, name node. If there is any issue with receiving the heartbeat, then it knows there is a problem with this, and then it assigns job to someone else. So the client periodically contacts and queries the job tracker. So there is always a constant conversation between these two guys until it receives the status that the job is complete. So this is the process of map reduce. Oh, I have the same one here. Sorry. So Hadoop system uses batch processing, which we already saw. And batch processing happens when a program runs from beginning to end. So whenever you are running something from beginning to end, imagine you are doing some uh, ML ML project. So you're starting from the beginning, from data collection until gaining some insights out of it. For example, if you're visualizing something, maybe you take the Titanic data, either the data analysis goes smoothly and task get completed, or something happens and we have to like stop it in the middle. The same thing happens to Hadoop system too. Here, the thing is there is no user interaction here. So you might have this question when batch processing is used. When all these computing tasks take more time, you will need more resources, more systems to process. So a good example, in most companies, especially in banks, most of the batch processing happens during the night or during weekends where most computers are free and most employees are not present. So this is where like batch processing usually takes place. And in companies, they do it in the year end when most employees are furloughed during that period. So there are something to simplify the map reduce process. Okay, I want to tell you something here. This map reduce process, whenever something happens, immediately it writes down. We can think of it like a 5-year old or 6-year old doing some basic mathematical problem in a notebook. So if they are adding 2 plus 2, 4, immediately they write it rather than keeping in their memory. So we have a thing called tight coupling. Tight coupling is a map is followed by reduce. And for this, we have the Hive and Pig. So Hive is a data warehousing system, and imagine it sitting on top of the Hadoop distributed file system. Sometimes people say, okay, Hadoop and MapReduce are same. Hadoop and MapReduce are not same. MapReduce is just a framework that works on Hadoop. Hadoop is always there. Hadoop is the backbone for all this to happen. And Hive is a data warehousing system, and it is on top of HDFS. This is again not a relational database, but Hive uses like a SQL like query, and it is called Hive QL. So This is mainly used in MapReduce job, and the process tends to be batch oriented, and the jobs are scalable. Like if the data is the quantity of the data, volume of the data increases, Hive is very beneficial there. But whenever you choose batch processing, it is going to be a poor choice for small jobs. If you have to find a subset of a bigger data, if you're using Hive, it is going to eat away all your time. This is not a very beneficial process. And then Pig tool is um, actually it's for a compiling high level scripting language, and the language name is Pig Latin. And this is used into MapReduce jobs for executions. So in concept, this is similar to Hive. It provides um, it also serves as a mean of producing MapReduce jobs without the burden of low level programming. So the primary difference between Pig and Hive is that Pig is a scripting language, which means it's procedural, while HiveQL is declarative. You can see the declarative and um, the difference between Java and Python. It's almost similar here. And declarative language allows the user to specify what they want and how data is manipulated. So this is very useful for performing data transformations, the one we do in ETL. So as a result, Pig is often used for producing data pipeline tasks that transform data in a series of steps. But we have something else that can supersede the MapReduce process, which is Spark. And we know Spark is the latest technology, and it is an open source project that was incubated at the UC Berkeley AMP Labs, and it was released in February 2013. This is a great alternative to MapReduce, and you can store data in several formats: CSV, JSON, HDFS, anything. And so here is where I want to mention the difference between um, a mathematical problem approached by a 6-year-old versus a 16-year-old. So the 6-year-old writes down everything in notebook, whereas a 16-year-old computes everything in mind and writes the final answer. So in Spark, you don't have to write data unless required. So it does in-memory computing, which is the which makes it very special. So the negatives of a map reduce thing is, after every map reduce operation, data is again written to the disk. Like it is written to the name nodes again and again. So what happens? It unnecessarily holds a lot of space. But Spark keeps things in memory. But you might ask this question: what happens if the in-memory capability is limited to a specific memory limit? In case if memory is full, the memory can be spilled. That is, it can be written to a disk. So in MapReduce, you do some computational instructions. So what happens is it keeps writing. For example, you just give some addition. I'm just giving you a small example. Maybe you want to add like thousands of numbers together. So what happens is, for every computer, maybe you give you like 10 numbers, and then okay, find the sum of 10 numbers, find the sum of 10 numbers, find the sum of 10 numbers, and all the 5 computers connected, they are finding the sum of those given 5 numbers specific to that node. And in the end, all of these are added together. So what happens is, like every addition, for example, the data node 1 has value like 1 2 3 4 5, then it like 1 plus 2 is 3, 3 plus 2 is 5. So it keeps on writing all these smaller chunks, which is unnecessary. You don't have to spend your memory for writing all these steps. So Spark, what it does is, like it does in memory thing, and unless you call for action, it is not going to write, or it is not even going to process the calculation. So call for action is very important in Spark, and that makes it very special. And there is something called Spark session and Spark context. Imagine you are going to do some cloud related work. What do? You try to connect to log into any of the cloud providers. For if it is AWS or if it is going to Azure, you're going to log in with your credentials, and then you will have a lot of things available to you. This is very similar here. So all these Spark jobs in organizational level, either they use cloud or maybe they have the infrastructure to perform. But I, as a user, I'm just a simple user. I don't have access to cluster. I only have my computer, and I only have one computer. So what happens? I log into Databricks, and then they have clusters available for me. It's available as a remote system, so it is all available. I'm only connecting my computer to that. So the first step is connecting to a cluster, which is very important. And then cluster is hosted in a remote system. Here it is in the case of Databricks. And then you check if there is existence of Spark. You can check. If you print SC, it is going to give you information. SC.version, it will give you the version of the Spark. And then Spark data frame behaves like a SQL table. Previously, I mean, even now you can use Spark has several types of syntax. One is for resilient distributed data set, RDD, and the other one is data frame. I can give you a simple example that can help you differentiate between RDD and DF. RDD is like you don't have a schema to understand what is happening. It will be like some chunk of data. If you look at it, you wouldn't even know what goes as a heading unless you know what you are doing. But for DF, um, you actually can um, compare it to the data frame in pandas. It's very similar. Even if you get a data set with no headings, you can have this information like, oh, infer schema is true. If you mention that, it is going to assume, okay, this first line or these are the specific names going to be given as the heading for that specific column. So you would know that. And Spark, so from the Spark context, we create the Spark session. So Spark session, so this analogy here, I put it here is Spark context is like a door. So that is the connection to the cluster. Once you open the door, you get all the thing that is available in that room. Maybe if that is your kitchen, you would get access to water, you can have your food, you can do whatever cooking thing you can do in the kitchen. uh, Recently the concept of Spark session has eliminated the effort to have a specific context. Like we have the Spark context, we have the SQL context, and there are so many other Hive context. So we don't have to have all these specifically mentioned, because Spark session is like a unified form. Like you enter into that, you get everything is made available for you. That is the um, benefit of the latest version. I think right now it is in version 3. So this is the basics of Spark for big data, and I hope this was beneficial to you. And I couldn't do the hands-on today because I ran into some issues yesterday, and I didn't want to um, let that happen. But in case if you are interested, and if we are together in group, I would post the hands-on which I do. I would take videos and I would share it with you guys. And thank you so much for giving this opportunity and opportunity to present during the final day. Thanks to Shazad and Susan for your continued efforts, and I thank you everyone for this opportunity. Thank you again.
Awesome. Thank you, Sukanya. Questions?
Hi, Sukanya. I'm Sandra. How are you?
Hi Sandra.
Sukanya, I've been studying Spark, and I am a little bit confused about an RDD and a data frame. Can you explain me the main difference between these two?
Okay, I can give you the explanation conceptually because I haven't worked with RDD myself. I have only experience with data frame. But the difference is with RDD, it does it doesn't have any specified schema. Um, a good example can be in data frame you have the table structure. Remember, so in each of these tables, a specific value is going to have its own norms. For example, if you are taking a column with heights, it is going to hold a float or double value. But in terms of RDD, it's going to be haphazard, and you have to specifically mention, you have to convert everything, like you have to standardize the data. But with data frame, it's going to be um, it is auto made. I don't know how to say that, but yeah, that's what I learned.
Okay, so I can say that in an RDD, you don't specify the structure, the schema, but in a data frame, you do?
In data frame, it is pre-built, but with RDD, you have to go and manually do that.
Okay, I got it. Thanks. And another question about the HDFS file system. These file systems, you can install it in a single computer, or you have to use it in a cluster?
So the main concept behind HDFS is having a cluster, having to work in a cluster because it is big data. You cannot uh, store in a single system, but they say you cannot means like you can do, which I have done that. I installed a local um, cluster, just created a virtual machine and worked on like two and processed a file and saved it as like two different outputs. Like after mentioning, it is possible, but it is very slow if you do it for a single computer.
Okay, just for testing purposes, maybe?
Yeah, for testing purposes, but it takes a lot of time.
Okay, thank you very much.
You're welcome.
Thank you. Questions? More questions? Anyone?
And apart from here, you can also post your questions in Slack. That way, I can also go check, find answers for you, and we can find answers together.
Yeah, that's a
Great, thank you.
good idea. If anyone hasn't joined the other Slack group, um, I'm not sure if anyone can share the link now, but then you can ask and we share it with you, okay? So
Yeah, sure.
if there's no other question for Sukanya, maybe we can end this part of our event. I'll stop recording now. Thank you, Sukanya.
Thank you.